if when you pop a prescription pill, we talked before about how it all doesn't metabolize, but for it to metabolize in the first place, it needs to dissolve, and then just how much of that, what dissolved, metabolizes is a whole other gambit. But, it's kind of a complicated calculation, but the fundamentals are what we're going to be doing today. You have lava lamps and just two liquids that won't mix at all, completely insoluble. But there's always a little bit of dissolving going on back and forth, but pretty much insoluble. You couldn't taste anything if it wasn't for solubility. And I remember being in some high school biology class, and we had little droppers full of sugar and salt, and we put them on different areas of your tongue, and you're supposed to be able to... They don't do that anymore. I don't know anything about biology, so I Google it and preparing for this, and that's BS. These taste buds are everywhere on your tongue. It's a combination of the taste buds and these other little cells, which are located in your nose, right? If you don't want to taste broccoli, all you do is just hold your nose, and you still feel the crummy taste of the stuff, the mushiness of it, but you really don't taste it. So it's a combination of the two, olfactory and taste buds. So, but without things dissolving in your mouth in the first place, you wouldn't even taste it. So we want to know how to write solubility reactions so we can actually predict just how much solid, or how much compound, or how much flavoring, or how much drug is going to actually dissolve. And that's a KSP reaction. And we've written Ka reactions, Kb reactions. We've written, like a Kw reaction. All these little subscripts. When there's a little subscript, you have to write the reaction a certain way. Otherwise, the Ka or Kb or Kw that you look up in a table, it's not right. So, how do you write a KSP reaction, solubility reaction? The solid is always a memory, a reactant, or a product. The solid has to go on which side? The reactant. It's a solid breaking up into its ions. The solid is always on the reactant side. And we don't have to do KSP problems on ionic compounds. That's all the homework is. That's all we're going to do. But we want to write the KSP reaction for that solid. Just some general solid. Now, to give you a hint, and we're just off of spring break, Destiny, what are the charges on X is the cation, Y is the anion. What's going to be the charge on that element X? Exactly. So the cations are positive, anions are negative, and on the X it's going to be a positive 3. Right? And everybody on the Y, that ion is going to be a negative 2. And you can do the math to verify it, right? 2 times positive 3 is positive 6. 3 times negative 2 is negative 6. Neutral. All the charges balance out. But that gives you a little hint, I think, on how to write this KSP reaction. Eddie, how would we write it then? Solid. That X2, Y3 is going to go to X with a positive 3 and Y with a negative 2. We're just not balanced. How many X's are there? There's 2 of them. How many Y's are there, everybody? There's 3. There it is. Now, we should write, but we never do, aqueous on ion. But we never do, and that's okay, because it's a charge, so I'm not going to take any points off. But there is something here that I would take a point off for, because it's important. The solid, that you have to write an S on. Okay. Because what don't show up in equilibrium constant expression? Solids and pure liquids. Right, so it's going to be important. Here's this container here. No, it's not barium phosphate. I have calcium phosphate. So, Jessica Rojas, let's pretend, what if I told you that I dumped some of this calcium phosphate in this water, pure water, at the beginning of spring break, and I just left it here, and now I'm showing it to you now. Would you say this solution is saturated? She's right. What does saturated mean? Can't dissolve anymore. Exactly. And the big hint there is look at all that solid laying on the bottom, right? So this is definitely a saturated solution. It's a dynamic equilibrium going on, and I'm trying to find an animation of it, but right, it is dissolving, but it's just precipitating or crystallizing at the same rate. They're balanced. Right? You're not. The net change is the concentration is the same of the ions in solution. It's saturated. What if, Sylvia, I took a little beaker and I scooped off some of this solution on top? Would that be a saturated solution? It's still, yeah, because it doesn't matter, right? It's just harder to tell, though, Sylvia, right? Because I take some, just like Nick is saying in Eldo, if I scoop some out of here, it's still, I took a saturated solution, it's still saturated, right? So nothing, it's just harder to tell because there's no solid laying on the bottom. Okay, so what we're going to be able to do today, by the end of the day, is I have 200 milliliters here. Just how much calcium phosphate actually dissolved in that water? We're going to actually calculate it, and we're going to get a number. What if I took some, let's say you get a number, pretend whatever the number is. Picture a number in your head. I take some of the solid on the bottom out. Is that going to change that number? It can't. Why? Because, well, it's already saturated, but what doesn't show up? Solids don't show up in equilibrium constant expression. So when you start doing all this math, take solid out of there, it doesn't matter. Saturated is saturated. That concentration of a solid is constant. You can't change it. Okay? We're going to look up KSPs, and they're all going to be tabulated. You can find a table for calcium phosphate. But how could those numbers change? Well, the amount of water, I can just get more to dissolve that. It's temperature, right? Temperature is how you change equilibrium constant. If I add more water in here, I'm not going to change the equilibrium constant. I'm just going to get more dissolved. So I do products over reactants, I get the equilibrium constant number. Okay, so let's try this one. Barium phosphate is slightly soluble in water. Write the solubility reaction. So go ahead and write it. Write the solubility reaction. Right? Remember, that's solid going to its ions. For barium phosphate. Now here we have a polyatomic ion, phosphate, but it's written in parentheses, so it's kind of easier to tell what it is. And you should forget what the charge is on the phosphate. Just look at the formula. It's there. Nope. If you write water, you have to write H2O on both sides, and this ends up canceling out anyway. So the solid goes to its ions. So Javier, what did you write on the reactant side? Yeah, perfect. You wrote, oh, hopefully, and a little subscript S. Okay, then on Pablo, on the the products. 3 barium. Yep. Perfect. And 2 phosphate. Right, the equilibrium constant expression for this reaction. So that's just what over what? Products over reactants. So write that. Write the KSP expression for this. Hopefully you're going to leave out solids. Yep. So, Vanessa, what did you write on? Something over something. Yeah? Perfect. She cubed the barium concentration. And then keep going. Whoa, it's both barium and phosphate are products, so they both be up on top, right? Squared. And that's all over 1. Right. So this guy, he's just a number that you get from a table. Okay. Get those KSPs from. But that, like I said, that number's going to be messed up if you don't write the reaction the right way. It has to be the solid going to its ions. Otherwise, that number isn't going to fit what you just wrote. So the homework is pretty much going to be find the solubility of barium phosphate. The trick is, Amanda, when solving solubility problems, solubility is always the X in probably what? Anybody help her? Ice. The X in ice. That's all we're after, the X in ice. We'll have our answer. Hey, when do we get our X in ice? Let's pretend, Genevieve, that the question is find the solubility of barium phosphate. Okay? And so we have to get the X in ice. Oh, you already wrote the nice reaction up there. What would be the units of our answer once we got it? Once we finally figure out what X is, what would be the units of our answer? Molarity. Molarity, right? So when you finally get your X, now what's molarity? Moles over liters. But here's where I think it gets confusing. Because that's nothing new, right? We make concentration tables. But it's moles of what? Look at this reaction you just wrote. We're going to do ice on it. Juan's right. It's moles of the solid. That you got to remember. X is the solubility. It's the solubility of the solid. So when you get your X, it's going to be in moles of, well, in this case, barium phosphate per liter. All right? Or big M of barium phosphate. Remember that. Remember that when you write a KSP reaction, it's solid going to the ions. Then when you finally do get X in ice, it's the molarity of the solid. Okay? All righty then. Let's try one of these. Find the solubility of calcium fluoride in water. And I could have made you look up the solubility, the KSP for it, Aldo, but I didn't. You find a table and calcium fluoride is 3.4 times 10 to the negative 11. Solubility, so X in ice. What reaction are we going to do ice on? Although, what reaction would you write? CA. Yeah. The first one's always positive. Cation's always first. Ca plus what though? Plus 2. Good. We'll keep going. F minus, but 2 of them. Yeah. We have 2 fluorides. So we have to have a stoichiometric coefficient of 2. But the subscript on the calcium is a 1, so the fluoride's just a negative 1. Or you can look at all the halogens. They always have negative 1 charge. we want to do X and ice, Nick. So before we start plugging in numbers, we should put dashes where? Otherwise, you're playing with fire. On the whole reactants, because if you don't do that right away, you could forget. No. Do we have, Jessica Vaughn, anything there initially to put in the I row? It's just pure water. It's just pure water. So we'll just put dashes. Do you see in part B or C here where you're not going to be putting dashes? Ray, in that initial row? For C, you see what he's looking at? The common ion effect. I don't even like the name common ion effect. It's just Le Chatelier. Because if we start out with which ion now? Fluorine. We're going to have to put what number in the I row for fluoride. Now, let me try to confuse you. Jessica says 0.1. I say, oh, no, it's 0.2 because look at that 2 right there. Which one's right? Yeah. The initial concentration of fluoride is not 0.2. The initial concentration of fluoride is 0.1. That's the number that would go there. Now, we're not there yet. I'm just saying that's what's coming. Okay? So we kind of... The sodium's only there because, yeah, you need to have some kind of solid, and it's completely soluble, like Nick said. So you dump in a little bit of sodium fluoride, it's not a KSP problem. It's all going to completely dissolve. That's that solubility rule where group number 1, all completely soluble. Let's see how good your memory is. I don't want to start out with a number here. I want to put a dash here. I want to end up putting a number under the calcium. See what I'm getting at? Okay, I want calcium. What anion goes with any cation completely dissolves 100% every single time? Starts on N. That's a cation. We need an anion. N-I-T-R-A-T-E. Nitrate. You put nitrate. Right? That should be a 2 down there. You put nitrates with anything, they completely dissolve. The reason why I'm getting that is when you look at this 0.1 sodium fluoride, right? You don't care about the sodium. It's just there to get the fluoride in. In this case, you don't care about the nitrate. It's just to get the calcium in solution. Okay, so just get used to that. The same solubility rule they're going to be using again and again and again. Okay, so we're not there yet, but that's what's coming. We have nothing there initially, pure water, so they're all dashes. We handle our change row, Matteo. How do we do that? Oh, you're so close.
Oh, I'm sorry.
2x, right? And then the E row, we just add stuff up, Mariella. So you just have, because x and nothing is x, 2x and nothing is 2x. Okay. Here's all of our answers. If they wanted to know the equilibrium concentration of fluoride, you just find 2x. But they're not. Now, look at this, kind of messy, though. They want grams per liter. Let's worry about that later. Let's just get our X and ice. Let's just get our X and ice. Okay. So, Victoria, what would be your next step to get X and ice? Yeah, the KSP. Set it up to equal to the KSP, she says. KSP is 3.4 times 10 to the negative 11. Let's not skip any steps. You just got off spring break. You're playing with fire if you start skipping steps. So what should we write here in the next one? What I'm after is don't write in terms of x's right now. Write the complete KSP expression. In brackets. And then, good, F minus squared. All right? Do you see why you do that? Because now we're going to have what times what? X for the calcium. Good. And 2x for the fluoride. But you're not going to square. You're not going to forget to square it if you wrote F minus squared. Okay. So we end up with what? X Shelby times 2x quantity squared. 2x third. She is so close. Yeah. It's really x 4x squared. So she's Victoria 4x to the third. She's right. That has to equal 3.4 times 10 to the negative 11. Now we got to solve for x, Alexa. How would you do that? Yeah, I divided both sides by 4. Good. Then what? Oh, yeah. Now, it depends on your calculator and what it can handle here. Let's divide by 4 first. If I divide by 4, show you a little trick here. 3.4 times 10 to the 11 negative. Divide it by 4. You get about 8.5 times 10 to the negative 12. Now, you have a couple choices here. If you're using the calculators that I checked out, you have a cube root button. You can use it. But let's say you don't. You could take both sides to what power? 1/3, and that would work. If it was x squared, you take both sides to a half. If it was x to the 5th, take both sides to the 1/5. Okay? But it's x to the 3rd, so you take both sides to the 1/3. Your cube root. And we have it, so I'm going to use it. 2.04 times 10 to the negative 4 is what I got for my x. Okay, you should get that on your calculator, regardless how you do it. She divided both sides by 4. That's what I forget. Someone told me to do that. Okay. Mallory, what units are we in, though? Yeah, you hear? You got to go from moles per liter to grams per liter. So we have 2.04 times 10 to the negative 4. We should maybe put a big M there so you can remember that, right? Big M is moles per liter. But moles of what? The solid, which is CaF2. How do we go from moles to grams? What's the technical word, Destiny? What's the technical word? We're going to be using the periodic table, but someone's saying it. Molar mass, right? Use a technical jargon. I think it helps you remember this stuff. You got to use molar mass. So in a mole of calcium fluoride, I got to add up a calcium and 2 fluorines. So the calcium is about 40.1, right there, number 20, plus fluorine is around 19, but I have 2 of them. I get about 78.1. Okay, so take that times 2.04, that's 10 to the 4 negative, about 0.016 grams of calcium fluoride per liter. So if you have exactly 1,000 milliliters, exactly 0.016 grams of calcium fluoride will have dissolved. Okay. Make sense? Question's changing a little bit. To find the solubility of calcium fluoride, so still X in ice, Eddie, but now it says in 0.1 molar sodium fluoride. We want the final answer in units. But what changed? Yeah, so this number is going. This 0.1 molar, is going to go where? The initial for fluoride. Exactly. So go ahead. Put in the initial for fluoride. See how that changes your answer. Now notice something that's really, really nice. Oh, let's back up a little bit. See, did we screw up here? Look at this. Do you remember this? 10 to the negative 11. We can drop x's, right? Does that have any effect over here?
We're doing it on the reactant side.
Dropping x's. You have to have something for it to drop from, right? There's nothing to... You can't just have an x and a 2x. You're not adding x or subtracting x from a really big number. So there's nothing to drop. Otherwise, we would have. So we didn't do anything wrong. We're fine. Now, in this problem, you're going to see, oh, yes, excellent. I have 10 to the negative 11. I can drop some x's. Okay? If you're adding or subtracting x or 2x or 3x, 4x, you can drop it. So write the KSP reaction. Fill in the ice table, taking into account what Nick said, that now you have initial fluoride. Set up the KSP expression. Solve for x. Convert it to grams per liter. You're done. We're going to do the exact same thing. There is right here. Except now we're going to have a number to put right there. No. Everything. Yep. It's going to change your x big time. So, write your reaction. Fill in the ice table. Okay. So hopefully you're on that track. All right. We're supposed to worry when it's 10 to the negative what? 10 negative 5, negative 4, big time problem, right? 10 negative 5 is getting iffy, but okay. Oh, I did, didn't I? Thank you very much. Okay. So now we can drop the x. Notice how now 0.1 looks like a small number, but it's not. If you're talking about 10 to the negative 11, this is only 10 to the negative 1, right? It's what? 100 billion times smaller is x, so nothing. We can drop that 2x. Notice this x in front. You can't drop it. There's nothing. You're not adding this or subtracting it from anything. There's nothing to drop. Okay? Because you see how you can't drop that x. If you're adding it or subtracting it from something, you could. But it's like, pretend this is a really small number. You take a really small number times something, you get a big different answer. You can't drop that x. The 2x you can drop. This is what you drop. So we end up with x times what? 0.01 or 0.1 squared, so we don't skip anything. Right. Math is a lot easier now. No cube root, no quadratics. Solve for your x. Convert it to grams per liter. See what you get.
So how come you were able to drop it inside over there?
I'm adding 2x to a big number. You can only drop x's if there's something to drop it from. If you're adding or subtracting x from a number. This is 0.1 plus 2x. X is, you multiply it times 2, you get a really, really small number. You add it to 0.1, you essentially get 0.1. Do it to the outside. Take x as a really, really small number. You take it times whatever this is, it's going to be a big difference. It's going to make that whole thing really small. So you can't drop that outside x. It's not dropping. That's erasing. You can't do that. So you should end up with about is it working here? Why is it working? Why isn't it writing? 3.4 times 10 to the negative 9 is my x, right? Convert that to grams per liter. Now that's moles per liter. And you said a mole was 78.1. Okay. So about 2.7 or so times 10 to the negative 7. Okay. Did everybody get it? Did you guys get it? Okay. If we had, let's put numbers in for, Jasmine's wondering about, a lot of folks are still wondering about this. Let's say we had x times, just put it at 0.1 plus 2x. Let's say x is, I don't know, it has to be really, really tiny so you can drop it, right? Let's put a number in there. So if you take 2 times that number, right, because 0.1 plus 2x, 2 times that number, you get all these O's and a 6. You add it to 0.1 on the calculator, you get 0.1, and then all those zeros and a 6, pretty much still 0.1. Okay? Does that make sense so far? So that's why this guy's okay to drop. Is everybody with me so far? He's okay to drop. Now let's try putting this number in for this x. Right? We said that our final answer here for 0.1 plus 2x is 0.100006. If you multiply that times 0.0003, do it and prove it to yourself. You're going to get a very different answer. You drop this x, you're not going to get, you change things. You drop the 2x, you don't change anything. Do it on your calculator. Prove it to yourself, Amanda. Prove it to yourself. Take 0.1, right, 006, multiply it times 0.50 and a 3. You're going to change things. Okay? If you don't believe me, you have to prove it to yourself and do it. You cannot drop an x if you're not adding or subtracting it from something. There has to be something to drop it from. Okay? There has to be something to drop it from.
What about if we can't drop the x?
If you have 10 to the negative 4, this whole thing equals 10 to the negative 4. We've done that. You can't drop anything. Now you have there's a Q, quadratic equation. You have to get in the form x plus c equals 0, substitute in the quadratic formula. Our limit, help Jasmine out, what's our limit? Negative 5. You don't want to see 10 negative 5, 10 negative 4, 10 negative 3, 10 right? Anything big. You don't want to see it. Because that means, I can't drop anything. Okay. And why is that? Because then x is big. You add 0.1 plus 2 times a big number, you're not going to get 0.1 anymore. Okay? All right. One more. We have a couple minutes. This question right here. You're going to see this in the homework. It's a twist. They want you to calculate KSP. We could just look it up, right? Find magnesium oxalate in the table, look it up, but you're not going to get any points. You have to calculate it. Now, you should get the thing is what's in the table, but you can't do it. How would you do this? Exactly. Did you hear Nick? You have your x. You have your x. Because solubility is the x in. So go ahead and write the reaction. Write the KSP in terms of, product over reactants, all in terms of x. But now, like Nick said, you know what your x is. Just substitute in. Because it's the solubility. The solubility is that number. What's the solid? The solid is magnesium oxalate. So it'd be Mg. Now, if you're really good at this, you're going to remember Mg is a +2, and oxalate is a -2, but it really doesn't affect anything. And then you do ice on it. Solid all the way down. There's nothing there initially. X and X, right? You end up with KSP. If you can really see this and jump way ahead, you end up with KSP equals X squared. Pretty much you're just going to square that 0.0093 and you're going to have your answer. Okay. Fill in the ice table. If you don't see it, fill in the ice table and write the KSP expression.
Yeah. There's the KSP. It's just
Yeah.
All right. So you pretty much just end up squaring the x, and you'll have your answer. And you notice how they could even throw another twist in this. If x was in what units, you'd have to do some converting. Yeah, if x is in grams per liter, you got to convert it to moles per liter before you can do this. Right. Okay, so you've got everything covered. Come by and ask some questions. If any of this doesn't look right,